So let's look at this second matrix with it, which is 3 by 2, and it's reduced to echelon form. We saw that the reduced to echelon form will just be 1, 0, 0, 0, 1, 0, because we can see that there are only two columns and they're not multiples of each other. The multiples of each other thing only works when we're dealing with only two columns. If I had a third column here, notice if I had the matrix C and I made it 1, 2, 3, and then 2, 5, 6, and then I put a third column, 3, 7, 9. No one column is a multiple of the other columns, but the third column is a linear combination of the first two, right? Wait, 1, 2, 3, 2, and 5, 7, 3, and 6, yeah. So we can't use the multiple things because there are 3 vectors. Oops, with 3 columns, 3 vectors. We can't use the multiple thing with 3 vectors. So the reduced echelon form here, we can get the first 2 columns. Since the second column is not a combination of the first, is not a multiple of the first column, I know that that's going to be the case, but then I would have to figure out how if the third column is related to the first 2. And then we can see that the third column is just the first. I just added the 2 together to make it real obvious. And so we can see pivots and then pivots. So we can't use the multiple thing with 3 vectors. That's one of the things I want to make sure that we point out. If you're saying that one vector is not a multiple of the others, you also have to point out that there are only 2 vectors in play. Any questions? So that response, they're not multiples of each other, is important. It's important to include the qualifier. There are only 2 columns and they are not multiples of each other. So well done. 1,000,000 points to everybody. All right, so what we notice is that B, the matrix B, C was a side matrix. We just want to, I just used that matrix and we might go back to it. The matrix B has a pivot in every column, but it does not have a pivot in every row. So we see that B does not have a pivot in every row. B does not have a pivot in every row. B does not have a pivot in every row. This is going to tell us about whether an equation is consistent, whether the columns of B span, or whether the transformation is onto. And it's going to be no for all those. As a set of vectors, we can say that the columns of B do not span R3. So the columns of B do not span R3 because B does not have a pivot in every row. We don't have to bring up an equation, but an augmented matrix, the augmented matrix and I'll put B, and I won't use B, I'll say Q. The augmented matrix BQ might have a pivot in its rightmost column. So because B does not have a pivot in every row, the augmented matrix BQ might have a pivot in its rightmost column. But the only way we can make that conclusion is by pointing out that B does not have a pivot in every row. That's what allows us to say that this augmented matrix might have a pivot in the rightmost column. If you just said that the columns of B do not span R3 because this augmented matrix might have a pivot in the rightmost column, I get to ask, why do you know that? The reason that you know that is that B does not have a pivot in every row. Since there's no pivot in, there's not a pivot in the third row, there might be a pivot in the rightmost column of an augmented matrix with B as a coefficient matrix. What we can say also is that bx equals Q is not consistent for all Q in R3. That's just the equivalent of what we say when we say that the columns of B do not span R3. So we'll say that bx equals Q is not consistent for all Q in R3. Because B does not have a pivot in every row. And we can use the same explanation that we had before. The augmented matrix for this matrix equation might have a pivot in the rightmost column. It also might not, but it might have a pivot in the rightmost column, so it's not consistent for all Q in R3. We could equivalently say that bx equals Q is inconsistent for some Q in R3. We could also say that bx equals Q. This is a very risky way to say it. Bx equals Q is inconsistent for some Q in R3 because B does not have a pivot in every row. This is a very risky way to say it, because if you just say Bx equals Q is inconsistent and end it there, I'll say, but Bx equals 0 is consistent. Bx equals 0 is always consistent. So we would not want to say that that Bx equals Q is inconsistent for all Q in R3, because that's just not true. That makes sense? I almost used the word it. That was close. So Bx equals Q is inconsistent for some Q in R3. The important thing to note here is that English usually allows you to take not consistent and replace with inconsistent, but not here. This is a precise language, and we got to be very careful about how we say things, because we're not negating the consistent parts. We're negating consistent for all Q in R3. This is what is an important part of the statement, and that was one of the comments that I made on some of your answers. You stopped at consistent, but that's not what we're concluding. Consistent for all Q in R3? Oh yeah, not that. Not that whole thing. So what we have to think about is consistent plus for all Q in R3. If you put a negative in front of that, you can distribute the negative. Negative consistent is inconsistent. Negative for all Q in R3 is for some Q in R3. Does that make sense? Not consistent plus for all Q in R3. And we have to distribute the not. So if we distribute the negation, it's not consistent is inconsistent. For some. Because not all, for all is for some. That's really sloppy logic as far as, not sloppy logic in writing the sentences, but thinking about it as plus. But it works well enough. All right, the important thing to remember is that Bx equals Q is always consistent for some Q in R3, because Bx equals Q, Bx equals 0 is always consistent. So always remember. Notice that it's not useful except for saying that bx equals 0 is always consistent, it's not really helpful for making conclusions. Things that are always true are not helpful for making conclusions. No, we cannot say that bx equals q does not have a unique solution. We could say that bx equals q does not have a unique solution for all q in R3 because bx equals q does not have a solution for all q in R3. It's important to drop the unique, because are you saying it's the solutions aren't unique, but there is one for all q in R3? Or is it that it just doesn't have a unique solution? So if you throw unique in there, why are you talking about unique when we're talking about pivots and rows? Does that make sense? What are you negating in your statement? So you are correct. Bx equals q does not have a unique solution for all q in R3 because bx equals q doesn't have a solution for all q in R3, unique or not. So it's troublesome to include unique in that conclusion because you're not being clear on what's being negated. Any questions? Comments? Snide remarks? All right. We can make, since B does not have a pivot in every row, we can make a conclusion about a linear transformation. We could say that the linear transformation that takes x to bx, oops, there we go. It doesn't have a pivot in every row. B doesn't have a pivot in every row, so B is not onto. What that means is that the range of B is a proper subspace of the domain. That's too much subspace, it's bringing too much stuff into it. The range of B is not all of R3. Oh, that's what we set up here. Bx equals q is not consistent for all q in R3. Any questions? Look at the matrix for its pivots. Use the pivots to conclude the columns span or are independent. The equation is consistent, inconsistent, or consistent with many solutions or unique solutions. And transformations being onto. Not onto would be not surjective. That is correct. Oh, there's even more we can say about the equation. Oh my gosh, how did I forget this? It's because I got to the bottom of the paper and I'm like, oh sweet, I could fit transformations in there. Then I remembered, oh dude, you forgot to say the unique solution business. So we have to back up a sec. It's so terrible because I talk so much, and then when I ask you to write answers, I'm like, oh, don't talk so much. It's just so one-sided. So if the equation bx equals q is consistent, then it will have the solution set. Sorry, I got distracted by my dog. He did a cute thing. He's over sitting in the other room. If bx equals q is consistent, it's not always, but if it is, then the solution is unique. The solution set will not have any free variables because there are no non-pivot columns in the coefficient matrix. The solution set to bx equal q will not have free variables because B has no non-pivot columns. If bx equals q is consistent, then this, and B has a pivot in every column, then the solution is unique. If the solution is not unique, then bx equals q is not consistent, or B does not have a pivot in every column. So it's because your not consistent is not the only thing there. There's an and there. Not consistent, and every if here, if bx equals q is consistent and b does not have a pivot in every row. Oh shoot, this is a column thing. I started rows. B has a pivot in every column. So if bx equals q is consistent, then the solution is unique. So you are right to question me on that one. But there's an and that when I say if bx equals q is consistent and b has a pivot in every column, then the solution set is unique. If the solution is not unique, then either bx equals q is not consistent or b does not have a pivot in every column. Since b does not have a pivot in every column, then if the solution set isn't unique, it must be because bx equals q is inconsistent. Any questions? I switched to columns and then I went to consistent. This is what happens when I'm like, oh, sure, I'll just do another example. So let's talk more about the columns. If B has a pivot in every column, the columns of B are linearly independent. Oops. If B has a pivot in every column, then the columns of B are linearly independent. It does. It turns the and, where it's a pivot in every column, and bx equals q is consistent to bx equals q. If we negate bx equals q is consistent and b has a pivot in every column, the negation of that is b does not have a pivot in every column or bx equals q is inconsistent. One of those things is not true. So if b has a pivot in every column, then the columns of B are linearly independent. That means one of the vectors is not a linear combination of the other vectors, or one of the columns is not a linear combination of the other columns. That also means the homogeneous equation, Bx equals 0, has only the trivial solution. So that is the other thing that means is that Bx equals 0 has only the trivial solution. So if the columns of B are linearly independent, that means that the equation Bx equals 0 has only the trivial solution. In the previous statement, we said if Bx equals q is consistent, then the solution is unique. Bx equals 0 is always consistent, so the solution is unique. So Bx equals 0 is always consistent, since we always have get the trivial solution. And so if the solution is unique, that means we only get the trivial solution. The only trivial solution thing is very effective and it's very efficient, but it's harder to use. So the columns of a matrix are linearly independent if the equation has only the trivial solution. So if Bx equals q is consistent, it can either have unique solutions or infinitely solutions. Otherwise, if it's not consistent, then you have no solutions. Right, that is correct. So an equation is consistent or not consistent? Not consistent is no solutions. So we wouldn't want to say unique solutions because there are none. Consistent means there's exactly one or infinitely many. Those are the three options that we have. Going all the way back to elementary algebra. That's why I like starting there. Any questions? The other thing that we can talk about, the other thing that we get to talk about is linear transformations. So we can say the transformation, the linear transformation, that goes x to b times x. Since b has a pivot in every column, this linear transformation is 1-to-1. Which is also injective. Injective is the other word for 1-to-1. What that means is that t of x equals t of y, then x equals y. This is the definition of 1-to-1. If t of x equals t of y, and t is 1-to-1, then x equals y. An example of a 1-to-1 function would be x cubed. -2 cubed is -8. Or if x cubed equals 8, we get only one real solution. -2. I can't remember what I said. If x cubed equals -8, then x equals -2. That's the only solution. Any questions? How's everybody okay? It's death by examples and writing lots of sentences today. That's what we're on about. All right. Those are all the things that we can draw about the matrix B that we wrote on the previous page. So let's pause the video here and talk about where we're going to go next.